In this video, we're going to talk about section 10.5, area and arc length and polar coordinates. And these topics are going to follow directly from what we talked about with area and arc length in rectangular coordinates and in parametric coordinates. So let's go ahead and get started here. Our objectives here will be to find the area of a region bounded by a polar graph, then to find the points of intersection of two polar graphs, to find the arc length of a polar graph, and to find the area of surface of revolution in polar form. Let's start with how we find the area of a polar region. Starting with the area of a circle, we have A equals pi r squared. If we have a central angle here that goes from 0 to 2 pi. But if we don't have that entire circle, then and we just have a sector, then we're going to think of, well, this pi here was half of 2 pi, so we need half of the theta, whatever that theta was. When we went 0 to 2 pi, we had half of it to give us pi r squared. So that's where this comes from. And then we're going to use this formula right here, and we're going to use the idea of a Riemann sum and integration, where if we start off with a radial line here at alpha, this is called a radial line, and a radial line here at beta, with beta being more radians than alpha is, then we can say that the radius r, which we're also going to call f of theta, of the ith interval, the ith sector here, which would be right here, somewhere in here. It doesn't really matter, you know, which one right here, but to go out to that point right there, let's say that this is f of theta sub I, and the central angle of the ith sector is going to be theta sub I, and we're going to have a delta theta of beta minus alpha over n. This is a beta minus alpha over n, just like we did b minus a over n for our delta x way back in chapter 4. Same kind of idea here. We're going to do the summation from I equals 1 to n, where we have n intervals here. And we're going to use this area of a sector of a circle formula. The 1/2 is a constant. The delta theta replaces the theta there as we look at each little interval. And we have the f of theta I squared, which is our r squared component. And that's going to be the 1/2 passes through, and the rest of this turns into a definite integral from alpha to beta of f of theta quantity squared. If you don't want to use the brackets around that, you can also call this a equals 1/2 alpha to beta of r squared d theta, like that. That'll be the same thing, and I'll probably write it like that more often. So here's that theorem. Now that we've developed the formula, if f is continuous and non-negative on the interval alpha to beta, and 0 is less than beta minus alpha is less than 2 pi, so alpha and beta have to be on the same rotation, beta needs to be bigger than alpha, then the area of the region bounded by the graph of r equals f of theta between the radial lines theta equals alpha and theta equals beta is a equals 1/2 of the integral from alpha to beta of f of theta squared d theta, which is the same thing as 1/2 integral from alpha to beta of r squared d theta. Again, the difference between beta and alpha has to be positive and less than 2 pi because they have to be on the same revolution. Note that you need to be cautious if f takes on both positive and negative values in the interval of alpha to beta. That's not going to happen in our first example here, and you might want to get your graphing calculator out to see what this looks like. When we have an odd number n in charge inside here, we're going to have the same number of petals, and we're going to take that 2 pi divided by that number of petals is actually going to give us how far apart the petals are going to be spaced. And so they're going to be spaced every 120 degrees here. I'm trying to draw them so that they're symmetric, and I'm terrible at drawing these things, which is why you have a graphing calculator. And then there's another one down here at 240 degrees. Like that, and I've drawn each of these a little different, and I shouldn't have. They should all kind of look the same, just having been rotated a little bit. But the radial lines we're interested in here are negative pi over 6 to pi over 6. And r is taking on only positive values in there. I'm going positive. I'm not walking backwards at all. If I'm facing a negative angle here, I'm walking forwards. If I'm rotating a positive angle here, I'm walking forward. So r is only taking on positive values in that interval. That's great. So I've got my formula set up here for my theorem, 1/2 integral alpha to beta of r squared d theta. I could use symmetry here to possibly help me and to get rid of this 1/2. If I see that I've got the same amount of area below as above, then I can go from 0 to pi over 6 and double it. That might be helpful here. So you decide which way you want to do it. If you want to use symmetry, I just went ahead and integrated from negative pi over 6 to pi over 6 here. And 3 squared is 9. So that gives me 9/2 on the outside, cosine squared of 3 theta d theta. I need to go ahead and use my power reducing formula here. Cosine squared becomes 1 plus cosine of 2 times this angle is cosine of 6 theta, and all that gets divided by 2. I take this 1/2 multiplier here and pull it out front to make a 9/4 integral from negative pi over 6 to pi over 6. 1 d theta plus 9/4 of cosine of 6 theta d theta. I need to do a u substitution here where u is equal to 6 theta, which tells me that du is 6d theta. So I need a multiplication by 6 on the inside here, multiplication by 1/6 on the outside out there is going to give me cosine u of du, integrates to give me sine of u evaluated from alpha to beta here. On the outside here, there's a common factor of 3. 3 goes into 9 3 times, 3 goes into 6 2 times. So I end up with 3 times 1 is 3, and 4 times 2 is 8. My multiplier is 3/8 on the outside there. This integral was just theta from negative pi over 6 to pi over 6. So that's going to be negative, or that's going to be 9/4 times the quantity, pi over 6 minus a negative pi over 6. Those negatives become positives. 2 pi over 6 is the same as pi over 3. 9/4 of pi over 3. 3 goes into 9 3 times, and I'm left with 3 pi over 4. Let's see what happens on the other side over here where I have 3/8 sine of 6 theta evaluated from negative pi over 6 to pi over 6. 3/8 times sine of 6 times pi over 6 is pi. Sine of pi is 0 minus sine of 6 times negative pi over 6 is sine of negative pi, which is also 0. 0 minus 0 is 0. 0 times 3/8 is 0. And my answer is 3 pi over 4. That's going to be measured in square units. And we only were asked about the area of a single petal here. If I were asked the area of all 3 petals, I would have to multiply that by 3. Now consider the polar equations. R equals 1 minus 2 cosine theta and R equals 1. Intuitively, we would expect that the way we would find the points of intersection would be to set the functions equal to each other, since they're both equal to R, and then solve for theta values for which they equal one another. And we would get values of theta is equal to pi over 2 and theta is equal to 3 pi over 2, which gives us this point of intersection here. Theta equals pi over 2. Let me see if I can change the color to make that brighter for you. Let's make that white. Theta equals pi over 2. And here, we're going the correct direction here. If theta is equal to 3 pi over 2, we're going in that direction. R is going to be positive in both cases. But we see another point of intersection over here where this cardioid that's coming this way and looping back around here hits this circle, is it? Yes, the circle of radius 1 right there. And we didn't pick up on that with just setting the equations equal to each other. So we definitely need to use technology to inspect and make sure that we didn't miss any solutions. Specifically, we missed the solution because it's a negative R value like that. So don't forget from our video last time that you can get negative R values for your point there, that I was at 0 and I was looking this way and I walked -1. So anything that's going to be on this polar axis right here is going to be tricky, whether it's at the pole or maybe over here like this. You are going to want to use technology to make sure that you don't miss any of those solutions. So we do have 3 solutions here. We found 2 of them just using algebra and trigonometry, but the other one we had to use graphing to see it. All right. Now we want to look at our first example here. And again, all these examples for this section should be straight out of the textbook. You can look at the images that are there to help you see what's going on. We want to find the area of the region common to the 2 regions bounded by the curves R equals -6 cosine theta and R equals 2 minus 2 cosine theta. So let me see if I can zoom in here and show you what we're talking about. So the area that is in common to them going to be inside both pieces here is what we're talking about. So we have this region that's shaded in blue, this region that's shaded in red or pink here, and then I have another copy of what's shaded in blue and what's shaded in red down here, but I don't need to find those again because I'm going to make use of symmetry to say that if I can find the area in this top half and then double it, that's what I want. That's everything that's going to be inside this circle and inside this cardioid. You see this kind of looks like a heart. It's called a cardioid. And so let's go ahead and work on that region 1. We're going to look for the blue part, and we're going to be interested in the circle there is going to help define that for us. So that's going to be our f of theta is going to be -6 cosine theta. And we're going to go from our radial line, theta is equal to pi over 2 to theta equals 2 pi over 3. Let's look at our picture once again to see how we came up with that. So here's our radial line right here, theta equals pi over 2. And here's our radial line, theta equals 2 pi over 3 right there. It's drawn for you in pink. And I'm interested in this sector right here that's between those two radial lines that is inside of this function. So that gives me A is equal to 1/2 of integral alpha to beta of r squared d theta. Just to show you this notation, because you'll see it in calculus 3, yes, we could keep writing pi over 2 to 2 pi over 3 each time along the way here, but we might choose a region name for it and draw it on the graph like we did here. Instead of the blue, we're just going to call region 1 or R1, or you might want to call it R1. R sub 1 might be good. Is typically how we're going to note this in calculus 3. And we're just going to show the graph to show the limits there, and we'll plug the limits in at the end. But we might just go ahead and write R1 for our boundaries here throughout the process of finding the integral, just so we don't have to write those limits of integration down every single time. So we're going to have an R1 is the way that I'm going to refer to this, R sub 1, and I'll call this one R sub 2. And switch back to blue here. Again, that R sub 1 there is going to be theta is between pi over 2 and 2 pi over 3. So when I get down here to where I'm doing my fundamental theorem of calculus and evaluating pi over 2 to 2 pi over 3, I go ahead and stick those limits of integration in. All right, so theta, f of theta was -6 cosine theta. When we square that, we get 36 cosine squared theta. Half of 36 is 18, and then I need to use my power reducing formula. Once again, 1 plus cosine 2 theta over 2. So half of 18 is 9. And then I split it up, 9 d theta, and then 9 integral cosine 2 theta d theta. I'm going to have to fix this u substitution right here for cosine 2 theta with a 2 d theta that I multiplied by 2 on the inside. So I need to divide by 2 on the outside, or multiply by 1/2 on the outside, whichever way you prefer to think about that. So that I end up with 9 theta from pi over 2 to 2 pi over 3 plus 9/2 sine of 2 theta from pi over 2 to 2 pi over 3. So this is 9 times 2 pi over 3 minus pi over 2. And I'm going to make a common denominator so that this is 4 pi over 6 minus 3 pi over 6 is 1 pi over 6. 9 times pi over 6 gets me 3 pi over 2 for the first part here. Then I want 9/2 times sine of 2 times 2 pi over 3 is sine of 4 pi over 3, minus sine of 2 times pi over 2 is sine of pi. Sine of pi is 0, so I'm not really interested in that piece, sine of 4 pi over 3, I'm going to be down here. Pi over 3 is my reference angle, and it's across from a root 3, and it's adjacent to a -1, and I've got a 2. So sine is going to be negative root 3 over 2. That's where that comes from. Minus the 0 doesn't matter. So 9 times negative root 3 is a negative 9 root 3. 2 times 2 is 4. And then we can leave it just like that for now. That'll be good. Now let's look at region 2, where our function 2 minus 2 cosine theta defines the region from 2 pi over 3 to pi. So from this radial line 2 pi over 3 to that radial line of pi, the cardioid defines the region there. And again, we're only going to pi because we're going to make use of the symmetry that we have and double our final answer here. So A is equal to 1/2 of alpha to beta, r squared d theta, 1/2 of region 2. So I'm going to call this here R2, and I'll make that red because it's red in the picture, not because it's a mistake or anything, but just to keep it consistent with the picture. Like that. And so we have something very similar to what we had before, just a little different because we have some subtraction here, that we have a common factor of 2 that can come out. 2 squared is 4, and then 4 times 1/2 is 2 on the outside. That's going to leave a 1 minus cosine of theta squared on the inside. And so that's going to be 1 minus 2 cosine of theta plus cosine squared of theta on the inside. There's a d theta. I just ran out of space over here. So we have a 2 d theta minus a 2 times 2 is 4 cosine of theta plus a 2 cosine squared theta that I need to use the power reducing formula for. 1 plus cosine 2 theta over 2. 2 over 2 cancels and leaves me with a 2 theta from 2 pi over 3 to pi, a negative 4 sine of theta from 2 pi over 3 to pi, a theta from 2 pi over 3 to pi, and I actually can't just throw those together because I'm not sure. Actually, I can. So this is going to be 3 of these since they have the same limits, but I didn't do that. I just went ahead and calculated it here. And then sine of 2 theta, the 1/2 up from 2 pi over 3 to pi. So pi minus 2 pi over 3 is going to be pi over 3, and then 2 times pi over 3 is a 2 pi over 3. Sine of pi is 0. Sine of 2 pi over 3 is going to be root 3 over 2. Remember, you find the difference. It's f of b minus f of a there. So we have negative 4 times a negative root 3 over 2. 2 goes into 4 2 times. So negative 2 times a negative root 3 is a positive 2 root 3. Now I have pi minus 2 pi over 3 is pi over 3. Again, that'll combine with this to give me a complete pi in just a second. And then half of sine of 2 pi is 0, and half of sine of 4 pi over 3, sine of 4 pi over 3 is a negative root 3 over 2. When I subtract a negative, I'm going to get a positive. So add these together. 0 plus root 3 over 2 is root 3 over 2. Take half of it, and I get root 3 over 4. Now, as I mentioned before, I have 2 pi over 3 and a pi over 3 that add together to give me a pi. I have a 2 root 3, and I have a root 3 over 4. Now to get my total area, I'm going to have to take 2 times, and I'm going to call this area 2 here. And I'll call this one area 1 up here. And I'm going to need 2 times area 1 plus area 2, which is what I did down here for my total area. So 2 times, and then it was, and I just wrote all this down, that this was, it's there, that's there, okay? So 2 times 3 pi over 2 is 3 pi. 2 times negative 9 root 3 over 4 is a negative 9 root 3 over 2. 2 times pi is 2 pi. 2 times 2 root 3 is 4 root 3. And 2 times root 3 over 4 is a root 3 over 2. That gives me negative 9 root 3 over 2 plus root 3 over 2 gives me a negative 8 root 3 over 2. And 2 goes into negative 8 negative 4 times. So I have a negative 4 root 3 here, plus a 4 root 3 from over here. We'll zero each other out. I have a 3 pi and a 2 pi is a 5 pi, and that is my correct answer. I have 5 pi, and don't forget this is square units. Scroll on down here. If we had tried to integrate this in rectangular coordinates, it would have been extremely messy. This note is in the textbook. You can look it up, but we would have had to go from something like -4 to -3/2, square root of 2 times the square root of 1 minus 2x, minus x squared minus 2x plus 2 dx. And there would have been some simplification that we could have done inside of that square root, but that's a big no thank you from me, that I don't want to deal with things this way. So when we see things that are more circular or oval or whatever in nature, that they appear to be sweeping a radius, and that radius may be changing as the angle changes. Polar coordinates are really going to help us here. And we're going to run into a lot of these types of polar regions in the future if you take Calculus 3. So it's going to be really, really helpful. We're going to expand this concept of polar into 3 dimensions, and you might have a polar region underneath, and you might have a height, or you might want to sweep another angle in a 3rd dimension. And so we can get either cylindrical or spherical coordinates from that. But it all starts with this understanding of polar coordinates in what used to be the XY plane, and you have the R theta plane instead. Quite a few of the problems in Calc 3 work that way. Why? Because you typically have sines and cosines to integrate, and powers of sine and cosine to integrate. And those are really a lot easier to integrate than messy looking things like this. All right, let's move on and talk about arc length and area of a surface of revolution in polar form. Again, this follows directly from our previous discussions on arc length and surface area. So theorem 1014 tells us that the arc length of a polar curve can be found by letting f be a function whose derivative is continuous on an interval of alpha less than or equal to theta less than or equal to beta. And the length of the graph of r equals f of theta from theta equals alpha to theta equals beta is, this is lowercase s for arc length, is equal to the integral of alpha to beta of the square root of f of theta squared, that's r squared, plus f prime of theta squared, that's dr d theta squared, or r prime of theta squared, d theta. So this is very, very much like what we have done already. Just be sure that the curve is traced out only once. The example kind of that I've given already is that as you drive your car from wherever to wherever, your tire only has a particular circumference to it, though that tire may spin around many, many, many hundreds, thousands, maybe even millions of times, depending on how long your trip is. Like if you're driving from here to California, you're going to have lots and lots of revolutions of your wheel, but that's not going to change the circumference of your tire. If you're trying to find the circumference of your tire, you're only going to want to go one revolution. So lots of times our limits here, not all the time, but you're going to see commonly that our limits will be 0 to 2 pi. Not always though. And our surface of revolution will be defined by letting f be a function whose derivative is continuous on an interval of alpha less than or equal to theta less than or equal to beta, and the area of the surface formed by revolving the graph of r equals f of theta from theta equals alpha to theta equals beta about the indicated line is as follows. So we can rotate about the polar axis. Remember, the polar axis is this initial side. When we have our angle, we have our polar axis down here. Or we can go through the line theta equals 2. So this is kind of like our horizontal axis. This is like our vertical axis. For the second one, it's kind of like whether we're rotating around y equals 0 or whether we're rotating around x equals 0. It's kind of what this is like. So we get the equation capital S here, and you might want to put the little lines on the end of it to indicate that it's a capital letter. Capital S is equal to 2 pi as a multiplier, integral from alpha to beta of f of theta sine of theta, square root of f of theta squared plus f prime of theta squared d theta. That's rotation about the polar axis. And the only thing that's going to change if we change to rotation about the line theta is equal to pi over 2 is this sine changes to a cosine. There, that's everything else stays the same. So capital S for surface area is equal to 2 pi, integral from alpha to beta f of theta cosine of theta, square root of f of theta squared plus f prime of theta squared d theta. So remember that sine goes with the polar axis and cosine goes with the line theta is equal to pi over 2. Again, make sure you're only tracing your curve once. So one example for each of these, for arc length, we're going to find the length of the arc from theta equals 0, from theta equals to 2 pi. Just told you that that's very common. Of the cardioid, r equals f of theta is equal to 2 minus 2 cosine theta. So there's your formula for arc length. Lowercase s is equal to alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. So our f of theta here was 2 minus 2 cosine theta. When we find f prime of theta or r prime of theta, we have 0 minus 2 times a negative sine theta is going to be a positive 2 sine of theta for our r prime. So we have lowercase s is integral from 0 to 2 pi of the integral of r, which is 2 minus 2 cosine theta, quantity squared, plus our r prime, 2 sine theta, quantity squared, d theta. And then we need to be very careful here how we square this. So 4 minus 4 here from 2 times 2. 2 times negative 2 is a negative 4, and then another negative 2 times 2 is another negative 4. Negative 4 times 4, negative 4 plus 4 is a negative 8 cosine of theta. and then a -2 cosine theta times another -2 cosine theta is a +4 cosine squared theta. And then we have plus a 4 sine squared theta. And I see a common factor of 4 here that will help me if I factor that out. So I get cosine squared plus sine squared, which is 1, and 4 times 1 is 4. So all of this right here, all of that is going to get replaced with a 4. 4 plus 4 is going to be 8. And then I have 8 minus 8 cosine of theta. So I'm going to take the square root of 8 out front, just factor it out there, and that leaves me 1 minus cosine of theta d theta, 0 to 2 pi for my limits. And this is kind of tricky. I've seen this quite a bit, so I see what's going on here, but we're going to have to get to 1 minus cosine of something appears in my power reducing formula for sine squared. So I set up sine squared theta equals 1 minus cosine of 2 theta over 2, multiply both sides by 2 to say 2 sine squared theta is equal to 1 minus cosine 2 theta. But I don't have a 2 theta, I have a theta. So what I need to do is I need to set up theta is equal to u over 2. So when I multiply 2 times u over 2, I get just plain old u. And I do that substitution over here and say that that's 2 sine squared of u over 2. And now I replace 1 minus cosine of something in here with 2 times sine squared of that something over 2, like this. This is sine squared in there. So I have another square root of 2 that comes out here, is going to give me 2 times 8 is 16. And then I have the square root of sine squared of theta over 2 is going to give me, I meant to get rid of this, is what I meant to do. There we go. So integral of sine of theta over 2, and I'm going to do my u substitution here. U is theta over 2, so du is 1/2 d theta. So multiply by 1/2 on the inside, 2 on the outside. 2 times 4 is 8. Integral of sine is going to be a negative cosine that gets evaluated from 0 to 2 pi. So this is theta over 2. A negative 8 on the outside. Cosine of 2 pi over 2 is cosine of pi. Cosine of 0 over 2 is cosine of 0. Negative 8 times cosine of pi is a negative 1, minus cosine of 0 is 1, so minus 1. Negative 1 minus 1 is a negative 2. Negative 8 times negative 2 is a positive 16. And this was arc length. So this is negative 16 plain old units, whatever those units are, but they're units of length. I think this is the last thing here. And again, this is straight from the textbook. Textbook used to have an animation for this. Kind of helpful, but I'll just tell you that it is helpful if you have 3D graphing software with this, where you can see what happens as you do the rotation to help you find these limits. I'll just tell you what the limits are. The textbook just tells you what the limits are, and I'll leave it at that. So the area of the surface of revolution, if you find the area of the surface formed by revolving the circle, r equals f of theta equals cosine of theta, which is going to be a circle of radius 1 that touches over there, has the center over here. We're going to revolve that about this, this line, r equals theta, and we're going to, our theta equals pi over 2. We're going to revolve about this axis theta equals pi over 2. So capital S is equal to 2 pi alpha to beta f of theta cosine of theta square root of f of theta squared plus f prime of theta squared d theta. And so we have a cosine out there because we're revolving about theta is equal to pi over 2. So capital S is equal to 2 pi integral 0 to pi. And you might say, why is it pi and not 2 pi? Because if we actually would draw this out and see it, it makes the full revolution here that's necessary within pi. It doesn't seem like that would work. It seems like you need to spin it a full circle around, but you don't need to make this pinched torus. You only need to go from 0 to pi. So cosine times cosine is cosine squared. The square root of cosine squared is 1 minus or plus a negative sine quantity squared is going to be plus sine squared d theta. Sine squared plus cosine squared is 1, leaving us with nothing but a cosine squared on the inside to be reduced with a power reducing formula is 2 pi 0 to pi of 1 plus cosine of 2 theta over 2. This 2 and that 2 can cancel, leaving with pi times the integral of 0 to pi of d theta plus, and then pi times integral 0 to pi of cosine of 2 theta d theta. I need to do a u du substitution and fix it by multiplying by 2 in the inside and 1/2 on the outside. That leaves me with S is equal to S representing surface area is equal to pi times theta being evaluated from 0 to pi. So pi minus 0 is pi, and pi times pi is pi squared. Then over here, we're going to have pi over 2 times sine of 2 theta evaluated from 0 to pi. So that's pi over 2 times sine of 2 pi, which is 0, minus sine of 0, which is also 0. 0 minus 0 is 0. And so that's a big fat 0 there. Pi squared minus 0 is pi squared. And this is going to be units squared for this problem. All right, that's it for this video. And this is the last main topic in Calculus 2. I think I'm going to come back and make another video for 10.6 as well, which is something you can talk about that's fun and interesting, but let's call that bonus content. So now that we're done with 10.5, we're done with all the main objectives from Calculus 2, and you should be ready to take your final exam in this class. If your teacher assigns 10.6, there's going to be a video out there for that as well. Hope you liked these videos. Take a look at 10.6 if you want to learn more about Kepler's laws and the types of orbits of stellar objects and how these parametric and polar equations play a role in that with the conic sections that we talked about from the beginning of this chapter. Have a good day.